A beam of light leaves the sun. 8 minutes later, it hits your face. But according to the equations of physics, along that entire journey, no time passed for the light at all. 0. The sun and your face were the same moment. That sounds impossible. And the truth is, it's more complicated than that. And far stranger. Tonight, we're going to cross 186,000 miles per second, break the rules of clocks, and find out what time actually does at the edge of reality. We'll ride inside a particle accelerator, sit inside a GPS satellite, and ask the question that breaks physics. What does light actually experience? If you enjoy this journey, hit like and subscribe. It helps more than you know. Brace yourself. We begin. You've heard it before. Someone says it casually, like it's obvious. Light doesn't experience time. A photon leaves a star, travels for millions of years, and arrives at your eye. And for the light itself, no time passed at all. 0. The whole trip happened in one instant. It sounds mind-blowing. It gets repeated in documentaries, in classrooms, in YouTube videos. And the wild part? It's almost right. Almost. The real answer is stranger than the slogan. And the slogan, as clean as it sounds, is sneaking a mistake past you. Here's the problem. That phrase quietly assumes that light has a point of view. It pictures a photon riding through space like a passenger on a train, watching the universe blur past, with a clock on the wall that reads 0 the whole trip. But physics doesn't actually give light that kind of experience. A photon doesn't sit inside a frame of reference the way you do. It doesn't carry a clock. It doesn't look out a window. The phrase is a shortcut, and shortcuts in physics almost always hide the part that's actually incredible. To understand what's really going on, you have to go back to the beginning, back to the rules that govern time itself. Because before you can understand why light sits at the edge of those rules, you need to understand what the rules even are. And those rules, it turns out, are nothing like what you learned growing up. Growing up, time feels obvious. Your clock on the wall ticks. A second is a second. An hour is an hour. The clock in your kitchen and the clock in your best friend's house 3 miles away run at exactly the same speed. Time is the one thing that never changes, based on where you are or how fast you move. That's the picture most people carry around, and it held up for centuries. Brilliant scientists built entire systems of physics on top of it. It felt so obviously true that nobody questioned it for a very long time. Then a young man sitting in a patent office in Switzerland started playing with an idea. What if that picture was wrong? What if time wasn't fixed at all? What if two clocks moving at different speeds through space would drift apart from each other, slowly, invisibly? But really, that young man was Albert Einstein. The year was 1905, and the paper he published that year didn't just change physics, it ripped out the foundation everyone was standing on. Einstein didn't say clocks run slow because of some mechanical glitch. He said time itself runs at different rates depending on how fast you move. Speed doesn't just change how far you go, it changes how much time you use to get there. That idea sounds insane, and when you first hear it, your brain pushes back hard. But here's the thing that makes it impossible to dismiss. Every experiment ever run has confirmed it. Every single one. Clocks on fast-moving planes land slightly behind clocks that stayed on the ground. Particles fired through accelerators live longer than they should. Even the GPS in your phone corrects for it every second of every day. Time dilation is real, confirmed, tested to extreme precision. And once you accept that time runs differently for moving objects, a door opens. A door to a question that goes much deeper than most people ever ask. If every moving object experiences time differently, what happens as you move faster? What happens as speed climbs toward the most extreme limit in the universe? What happens at the speed of light? That's where things start to break. And the answer is going to change the way you think about time forever. Most people think of time as a river. It flows forward. It carries everything with it. You can't speed it up or slow it down. You just ride it. Einstein looked at that picture and said it was only half true. Time does move forward, but the speed at which it moves, that part changes. Here's how to see it. Imagine two friends. Call them Maya and Jordan. They're both wearing identical watches, perfectly synchronized. Maya stays home. Jordan gets on a rocket and flies across the country at incredible speed, then turns around and comes back. When Jordan lands and they hold their watches side by side, something strange has happened. Jordan's watch shows slightly less time has passed. Maya's watch is ahead. They were apart for the same trip. They both experienced real seconds, real heartbeats, but their clocks disagree. This isn't a malfunction. The watches aren't broken. Time itself moved at two different rates for two different people. That experiment, in versions involving atomic clocks on airplanes, has been run many times. The result always matches. The moving clock falls behind. Physicists call this time dilation. Dilation just means stretching. Time stretches out for the fast-moving object. To everyone watching from outside, the fast traveler's clock appears to slow down. Now here's the part that trips people up. Jordan on the rocket doesn't feel anything weird. Her heart beats normally. A minute feels like a minute. Her watch ticks at exactly what feels like the right pace. Inside her own experience, everything is fine. The weirdness only appears when she lands and compares clocks with Maya. That's the key. Time dilation lives in the comparison. It's about what two different observers measure when they look at each other across different speeds. Inside your own frame, your own bubble of experience, time always feels normal. 1 second is always 1 second. So where does the difference come from? It comes from speed. The faster you move relative to someone else, the slower your clock runs from their perspective. The gap is tiny at everyday speeds. A car driving 60 miles per hour for an entire year falls behind by less than a millionth of a second. You'd never notice. But as speed climbs, the gap grows dramatically. At half the speed of light, the difference becomes noticeable. At 90% of the speed of light, your clock runs at roughly half the pace of a stationary observer's clock. At 99%, the gap widens even more. The math that describes this is called the Lorentz factor, named after the physicist who first worked it out. You don't need the formula, the picture is what matters. The closer you push to the speed of light, the more stretched your time becomes from someone else's view. And this stretching has no ceiling. It keeps growing and growing the closer you get to that limit, which raises an obvious question. What happens at exactly the speed of light? That's where the math does something disturbing. It doesn't just give a big number. It breaks. The equation reaches a point where the answer stops being a normal number at all. And that's the moment when light stops behaving like everything else in the universe. Something is waiting at that edge, something the equations weren't designed to handle. And to understand it, you first need to understand the one rule of physics that has never ever been broken. In 1905, Albert Einstein was 26 years old and working a day job reviewing patent applications in Bern, Switzerland. He had no laboratory, no telescope, no research team, just a desk, a mind, and a habit of asking questions nobody else thought to ask. That year he published 4 papers. Any one of them would have made him famous. Together they changed physics permanently. The one we care about is called the special theory of relativity, and the idea at the center of it is deceptively simple. It starts with just 2 rules, 2 postulates as physicists call them. The first rule: the laws of physics work the same for every observer who isn't accelerating. Whether you're sitting still in your kitchen or flying through space at thousands of miles per hour, the same physical laws apply to you. The universe doesn't play favorites based on your speed. The second rule: the speed of light in empty space is always the same for every observer, at every speed. no exceptions. That second rule is where the explosion happens. Think about what it means. If you're standing still and a ball rolls past you at 30 miles per hour, and your friend is running alongside it at 10 miles per hour, your friend sees the ball moving at 20 miles per hour. Speeds add up. That's how everything in daily life works. Light refuses to do that. If a beam of light passes you while you're standing still, you measure it moving at 186,000 miles per second. If you then climb into a rocket and chase that same beam at half the speed of light, you measure it moving at 186,000 miles per second. The beam does not slow down relative to you. The number doesn't change. This seems impossible. It broke the brains of physicists when they first encountered it. How can light always move at the same speed no matter how fast you're chasing it? Einstein's answer: because time and space themselves adjust to make it true. If the speed of light is constant, then something else has to give, and what gives is our assumption that clocks tick at the same rate for everyone, and that distances stay fixed. Einstein showed that time and space are not rigid. They bend and stretch depending on how fast you move. The universe bends the rules of time and distance precisely enough to ensure that everyone always measures light at the same speed. That was the revolution. Space and time weren't separate, unchanging things. They were flexible, woven together into something physicists would later call space-time. And the speed of light sits at the center of that fabric like a fixed nail. Everything else in the universe warps around it to keep that number constant. Einstein didn't need an experiment to find this. He found it by following the logic of two rules to their unavoidable conclusion. The experiments came later, decades of them. Every single one confirmed what he predicted from a desk in Switzerland with no equipment at all. But here's what Einstein's paper did not quite answer. It explained what happens to clocks and rulers as speed increases. It showed time slowing down for fast movers. It drew the limit at the speed of light. What it left wide open was the question of what happens right at that limit. What exists at the boundary? What does the universe look like from there? Answering that question requires a tool most people have never heard of. And it reveals something about light that goes far deeper than any slogan. Einstein's theory was beautiful on paper, but beauty in physics means nothing without evidence. And in the early years, the evidence was thin. The problem was speed. To see real-time dilation, you need to move fast. Really fast. Human beings in 1905 were traveling by horse, by train, by early automobiles. The fastest vehicles on Earth moved at maybe 100 miles per hour. At that speed, the time dilation effect is so small it's invisible. You'd need a clock accurate to a fraction of a billionth of a second just to measure it. Nobody had that kind of clock, so physicists waited, and the universe provided an unexpected testing ground. The sky itself. High above the Earth, around 15 miles up, cosmic rays from space slam into the upper atmosphere. These are particles traveling at extraordinary speeds, close to the speed of light. When they hit air molecules, they produce secondary particles called muons. Think of a muon as a tiny, unstable cousin of the electron. It lives for about 2 millionths of a second before falling apart. Here's the problem. Even moving close to the speed of light, a muon traveling for 2 millionths of a second can only cover about a third of a mile. The atmosphere is 15 miles thick. A muon produced at the top should disintegrate long before it reaches the ground. The math says it can't make it. And yet, muon detectors on the surface register them constantly, thousands per minute, passing right through the ground under your feet at this very moment. How? Time dilation. From our perspective on the ground, the muon's clock is running slow. Because it moves so close to light speed, time stretches out for it. What is 2 millionths of a second for the muon translates to a much longer window from our perspective. Long enough for the muon to survive the full 15-mile trip and hit the detector. The muons don't know anything strange is happening. Inside their own reference, Their clock runs normally, and they simply don't exist long enough to reach the ground. But from ours, they make it every time. Scientists ran careful measurements comparing the count of muons at high altitude to the count at sea level. The numbers matched Einstein's predictions almost exactly. The moving particles' clock ran slow. Time dilation was real. That was the first concrete, measurable proof outside a laboratory. Nature had been running the experiment in the sky for billions of years. Einstein's equations passed. Then came atomic clocks. In 1971, scientists loaded incredibly precise clocks onto commercial airplanes and flew them around the world. When the planes landed, the airborne clocks showed slightly less time had passed than identical clocks left on the ground. Again, exactly what Einstein predicted. That experiment has been repeated many times since, with even better equipment. The result never changes. Moving clocks fall behind. And here's what makes this permanent, and not just academic. Every time you use your phone for navigation, the satellites feeding it your location are running clocks that have drifted from the clocks on Earth. The engineers correct for that drift using Einstein's equations. Without the correction, your phone's navigation would be wrong by miles. Within a day, time dilation keeps your GPS working. It's not a theory, it's infrastructure. And if time dilation is real for objects moving at ordinary fast speeds, what happens when you keep pushing? What happens as speed climbs past anything a rocket can achieve and approaches the absolute ceiling of the universe? The answer stops being gradual. It becomes extreme. And then, at the very limit, something breaks. There's a question that always comes up when people first hear about time dilation. If your clock is running slow, do you feel it? Does everything around you seem blurry or sluggish? Does your heart beat slower? The answer is no, and that answer reveals something profound about how time actually works. Imagine you're in a spacecraft, moving at 90% of the speed of light relative to Earth. You're sitting in the cabin. You pull out your watch. It ticks normally. 1 second, 2 seconds. You make a sandwich, it takes the same amount of time it always does. You take a nap for 8 hours. You wake up feeling rested. From Earth, observers watching your ship through a telescope see something very different. Your clock appears to tick slowly. Every second of your time corresponds to roughly 2 seconds of theirs. You aged 8 hours. They aged closer to 18. But you felt nothing strange. Your heartbeat, your hunger, your thoughts, your watch, all perfectly normal inside the spacecraft. This is the central piece that trips people up. Time dilation doesn't feel like anything from inside. You only discover it when you land and compare clocks with someone who stayed behind. The difference is in the comparison, not in the experience. Why? Because physics is the same inside any smoothly moving frame. You can't do an experiment inside a spaceship moving at constant speed that tells you how fast you're going. Every physics experiment runs the same whether you're sitting still or flying at half the speed of light. There's no internal alarm that goes off to warn you. Think of it like being on a perfectly smooth airplane flight, with the window shades down. You have no sensation of moving. The food, the conversation, the clock on your phone, all normal. Only when you land and notice you've crossed 5 time zones do you realize how far you traveled. Speed doesn't feel like anything from inside. And neither does time dilation. Now, here's where it gets genuinely strange. The effect works in both directions. If you're watching Earth through your spacecraft window while you fly away at 90% of light speed, Earth's clocks appear to run slow to you. Their processes look sluggish from your perspective. Both observers think the other's clock is the slow one, and both are correct within their own reference frames. The disagreement only resolves when one of them changes speed, stops, and comes back. The one who traveled ends up younger. The one who stayed ends up older. That's called the twin paradox, and it's been tested. The traveling twin genuinely ages less. The experiment works. So time dilation is invisible from the inside, relative from the outside, and only finally settled when the travelers reunite and compare notes. This tells us something remarkable about the nature of time itself. Time is personal. It belongs to your path through the universe. Two people can share the same starting point, the same ending point, and still accumulate different amounts of past between them. The river metaphor is wrong. Time isn't a river everyone floats down together. It's more like a distance. Different paths through space-time have different lengths. The faster you move through space, the shorter your path through time, and the fastest anything can move through space, the speed of light. So what happens to time along the path light travels? That question leads somewhere the human brain was never built to follow. And the equations there do something nobody expected: 186,000 miles per second. Say that number out loud. 186,000 miles every second. To put that in your head, the distance from New York to Los Angeles is about 2,800 miles. Light covers that distance in less than 1/100th of a second. In one full second, light travels around the entire Earth about 7.5 times. In 8 minutes, it crosses the 93 million miles between the Sun and your front door. In 4 years, it crosses the distance to the nearest star beyond our Sun. For most of human history, nobody knew how fast light moved. Ancient philosophers assumed it was instant. Then in 1676, a Danish astronomer named Ole Romer noticed something strange while watching the moons of Jupiter. The timing of their orbits was off, slightly early when Earth was closest to Jupiter, slightly late when Earth was farthest away. He realized the difference was caused by light taking extra time to cross the larger distance. He was the first person to measure the speed of light. His estimate was about 124,000 miles per second, off from the real number, but in the right ballpark. For 1676, using just Jupiter's moons and a calendar, that was extraordinary. Precise measurements came centuries later. By the 20th century, scientists had refined the number so exactly that in 1983, the international scientific community redefined the meter itself using the speed of light. 1 meter is now officially defined as the distance light travels in a vacuum in exactly 1,299,792,458th of a second. The speed of light became the ruler the universe uses to measure space. But the number itself is only part of the story. What makes light speed special isn't how big it is. What makes it special is that it's the same for everyone. An astronaut moving away from Earth at half the speed of light and a scientist standing perfectly still in a lab both measure light moving past them at exactly 186,000 miles per second. The astronaut doesn't measure it moving slower because she's already going fast. The number stays fixed. Always. That constancy seems like a small technical fact. It isn't. It's the load-bearing wall of the entire universe's structure. Because if light always moves at the same speed for all observers, and speed equals distance divided by time, then the only way to keep that constant is for distance and time to change. Space and time have to stretch and compress to make sure the number holds. Every weird consequence of relativity, every clock that falls behind, every ruler that shrinks at high speed, everything flows from that one fixed rule. Light speed is constant. Space and time bend around it. This means light isn't just fast, it's different in kind from everything else that moves. Matter can move at a range of speeds. It can accelerate or decelerate. It can be slow or quick. But the speed it moves at is always a matter of comparison. You ask, fast compared to what? Light doesn't answer that question the same way. It moves at the same speed compared to everything. There's no compared to what for light. The number holds regardless of the frame. That uniqueness is what places light at a completely different position in the laws of physics. And understanding why that position exists requires looking at something even more fundamental. Something called a rest frame, and the unsettling discovery that light doesn't have one. Everything in physics depends on reference frames. That phrase sounds technical, but the idea is simple. A reference frame is just your vantage point, where you are, how fast you're moving, what direction you're facing. Your reference frame is the bubble of experience you carry around with you. You're sitting in a car. A truck rolls past at 60 miles per hour. From the sidewalk, both you and the truck are moving. From your perspective inside the car, you appear still, and the truck rushes by. From the truck driver's view, you're the one rushing past. All three perspectives are valid. None is more correct than the others. That's the beauty of reference frames. Physics works in all of them equally well. Now, here's the rule Einstein built everything on. Every observer in a smoothly moving reference frame will measure the speed of light in empty space at the same value, 186,000 miles per second. Every time, no exceptions. This rule had actually been sitting in the equations of electromagnetism since the 1800s. A scientist named James Clerk Maxwell worked out the equations that describe electric and magnetic fields, and those equations predicted that light moves at a fixed speed. The problem was that Maxwell's equations didn't specify fixed relative to what. Every other speed in physics was relative to something. Light seemed like it should be too. Scientists at the time assumed there had to be a medium filling all of space, something they called the aether, and that light moved at 186,000 miles per second relative to that medium. Different observers moving at different speeds through the ether should measure different speeds for light. In 1887, two American scientists, Albert Michelson and Edward Morley, ran an experiment to detect Earth's motion through the ether. They split a beam of light, sent the two halves in perpendicular directions, and looked for a difference in speed. If the ether existed, one half should move slightly faster than the other, depending on which direction Earth was moving through the ether at that moment. They found nothing, no difference at all. The result was identical no matter the direction. The ether didn't exist. Light moved at the same speed in every direction for every observer, full stop. Einstein was the one who stopped trying to explain away the result and instead accepted it completely. He made that constant speed the foundation of his entire theory. And once you accept that light always moves at the same speed for all observers, you cannot escape the conclusions that follow. Your intuitions about how speeds add up simply stop working near light speed. Clocks can't tick at the same rate for everyone. Distances can't be the same for everyone. The only way the mathematics holds together is if space and time themselves are flexible. This was not a strange guess Einstein made. It was the unavoidable outcome of taking the Michelson-Morley results seriously. The constant speed of light isn't just a fact about light. It's a constraint that the entire structure of space-time has to obey. Everything in physics bends around that constant, which raises a question that sat at the back of every physicist's mind once they absorbed all this. If light speed is the fixed limit everything else is measured against, what is light itself measured against? Every other moving thing has a rest frame, a speed of 0, a home position. What's light's home position? The answer to that question is where things get deeply strange, because light doesn't have one. You've accepted it. Light moves at the same speed for everyone, every observer, every frame, every experiment. Fine, weird, but fine. Now follow the logic one more step, because this is where the universe quietly dismantles everything you thought you knew. Imagine you're in a spaceship. You fire a ball forward at 60 miles per hour relative to the ship. Someone outside the ship, watching you fly past at 1,000 miles per hour, measures the ball moving at 1,060 miles per hour. Speeds add. This is basic, intuitive, and works perfectly for everything except light. Now, instead of a ball, you shine a flashlight forward. The light leaves your ship at 186,000 miles per second relative to you. The outside observer measures that same beam. Do they get 186,000 plus 1,000? No. They get exactly 186,000 miles per second. The speeds didn't add. The light beam moved at the same speed relative to both observers, despite those observers moving at different speeds relative to each other. For that to be true, distance and time have to be doing something behind the scenes. From the outside observer's perspective, your clock on the ship is ticking slower than theirs. Your rulers pointing in the direction of motion are shorter than theirs. Space and time are quietly adjusting so that when you both measure the same beam of light, you both get the same answer. The universe bends itself to protect that constant. Now imagine instead of 1,000 miles per hour, your spaceship is moving at half the speed of light, now at 90%. The outside observer still gets 186,000 miles per second for the light beam. Your clock has to run even slower. Your ruler has to compress even further. The adjustments get more extreme as your speed climbs. Now imagine pushing your spaceship to 99% of light speed. The outside observer still measures the light at 186,000 miles per second. Your clock is now running at a fraction of theirs. Your ruler is dramatically shorter. The universe keeps bending. It has to. The constant must hold. And here's the thing nobody says out loud in casual explanations. The bending has no limit on the way up. As you approach light speed, the adjustments become more and more extreme. Your clock approaches zero. Your ruler approaches zero. The math pushes toward infinity in some places and toward zero in others. At exactly light speed, the equations hit a wall. They don't produce a sensible answer for a massive object. They break. That breakage is the universe's way of saying something. It's saying that light speed isn't just the fastest speed available. It's the point where the rules governing matter stop applying. You're not approaching a high number. You're approaching a boundary between two different kinds of things in the universe. And everything you've understood so far, the dilation, the flexible clocks, the compressed rulers, all of that still involves objects with mass. Objects that can slow down, speed up, carry a clock and be assigned a reference frame. Light doesn't have mass, and that single fact places it in a completely different category. A category where the ordinary concept of a rest frame doesn't exist. To understand why, you need to understand what a rest frame actually is. And once you do, the reason light can't have one becomes obvious in a way that's almost more disturbing than the mystery itself. Every object you've ever touched has a rest frame. Every person, every planet, every grain of sand. A rest frame is simple. It's the perspective where you're sitting still. Right now, from your own point of view, you're stationary. The room around you is stationary. Everything is at rest relative to you. That's your rest frame. From someone's perspective out in space, you're actually moving at tremendous speed as Earth orbits the Sun, and the Sun moves through the galaxy, and the galaxy drifts through space. But inside your own reference frame, inside your own bubble, you're the one who's standing still, and everything else is moving around you. Every massive object gets this. A planet has a rest frame. A spaceship has a rest frame. Even a speeding bullet has a rest frame. It's the perspective where the bullet is standing still and the gun is flying backward away from it. No matter how fast something moves, you can always construct a valid frame of reference where that thing is at rest. This matters for time. Inside a rest frame, you can place a clock. That clock ticks. You can assign a time to events. You can say, this happened first, then this happened. You have a full, coherent experience of time passing because you have a valid rest frame to sit inside. Now think about what that requires mathematically. To have a rest frame, something has to be possible to stop, at least in principle. You don't have to actually stop it. The concept just has to make sense. For a massive object, it always does. In principle, you can slow a baseball down to zero. You can decelerate a rocket to rest. The idea holds. Light travels at 186,000 miles per second. Every observer measures that. Always. So ask yourself, could light, even in principle, be at rest? If light were at rest, it would have a speed of zero. But every observer measures light at 186,000 miles per second. 0 and 186,000 are not the same number. There's no frame of reference from which light is standing still, because in any frame you enter, you'd still measure light moving at 186,000 miles per second. There's no way to catch up to light. You can chase it at 99% of light speed, and you still measure it moving away from you at the full 186,000 miles per second. Every time. No exceptions. That means the concept of a rest frame doesn't apply to light. You can't construct one. Physics won't allow it. A photon has no home position, no state of rest, no frame where it's sitting still. It occupies a completely different category from everything with mass. Massive objects can have zero velocity somewhere. Light cannot. And this is the precise reason the slogan breaks down. When people say light doesn't experience time, they're picturing a photon riding in its own rest frame with a clock that reads 0, but there's no rest frame to ride in. There's no valid perspective where the photon is sitting still. The picture the slogan creates is physically impossible. The real answer is stranger. And to get to it, you need to look at what the math actually says when you push toward light speed. Because when you approach that limit and watch what the equations do, they don't just get extreme. They do something that has no parallel in ordinary physics. You can stop a car, you can stop a satellite, you can, in principle, slow a star down to 0 relative to some distant observer. You cannot stop light. And the reason cuts straight to the heart of what light actually is. Light is an electromagnetic wave. That means it's made of an electric field and a magnetic field, each one driving the other forward. When an electric field changes, it creates a magnetic field. When that magnetic field changes, it creates an electric field. They leapfrog each other through space endlessly, and the speed at which that leapfrogging happens, that's the speed of light. The wave doesn't need a medium to travel through. It doesn't push off anything. It sustains itself. The electric field becomes the magnetic field becomes the electric field again. And each transition carries the wave forward. If you slowed that wave down, the leapfrogging would stop. The fields would collapse. The light would cease to exist. You can't have light at rest, any more than you can have a running river that isn't moving. A river at rest isn't a slow river. It's just water sitting in a field. Light at rest isn't slow light. It's nothing. This is why every observer always measures light at the same speed. It's not a coincidence or a weird trick of measurement. It's what light is, an electromagnetic oscillation propagating at a fixed rate set by the properties of space itself. The speed isn't incidental to light. It's essential. Two fundamental constants set that speed. One describes how strongly electric fields act through space. The other describes how strongly magnetic fields act through space. Multiply them together in the right way, and you get the speed of light, written right into the fabric of the universe. Change either constant and the speed of light changes, the universe would look completely different. So light moves at 186,000 miles per second, because that's the rate at which electromagnetic fields propagate through the vacuum. Not because something is pushing it, because that's the speed baked into the structure of space. And because light can't slow down, it can never be at rest. Because it can never be at rest, it has no rest frame. Because it has no rest frame, it can't carry a clock in the ordinary sense. Because it can't carry a clock, the question of what time a photon experiences can't be answered the same way you'd answer it for a rock or a person. The slogan "light doesn't experience time" is pointing at something real. The geometric path that light takes through space-time is genuinely different from the path matter takes. Along a light-like path, physicists say no proper time elapses. Proper time is the time measured by a clock riding along with an object. For any massive particle, that clock ticks. For light, the concept doesn't apply because there's no valid clock you could attach to a photon. So the precise statement is that no proper time is defined along a light-like path. The slogan compresses that into light doesn't experience time, which is catchier but loses the important part. The important part is that this isn't about a photon having a strange frozen experience. It's about light occupying a different category in the geometry of space-time entirely. And to see why, you need to look at what the equations actually do when speed approaches that limit. Because at the edge, the math reveals something nobody talks about in casual explanations, something that makes the whole picture click into place. You've been building toward this. Every chapter has moved one step closer. Now here's what the equations actually show when you push toward light speed. The formula for time dilation has a number inside it. That number, called the Lorentz factor, tells you how much slower a moving clock runs compared to a stationary one. At low speeds, the factor is almost exactly 1, barely any dilation. At half the speed of light, clocks run at about 87% of their normal rate. At 90% of light speed, they run at roughly 44%. At 99%, about 14%. The closer you get to light speed, the smaller that percentage gets. The clock runs slower and slower relative to a stationary observer. At exactly 100% of light speed, what does the formula give you? The moving clock, as seen from outside, runs at 0% of normal speed. Elapsed time on the moving object, measured from outside, equals 0. That's where the slogan comes from. Push the math to the limit, and the proper time along a path, moving at light speed, comes out to 0. Emission and absorption of a photon, the moment it's created and the moment it's destroyed, are separated by 0 elapsed proper time in the equations. But here's the critical piece that most explanations skip. That result only makes sense for light itself, for massless particles that always move at exactly that speed. For a massive object, the formula doesn't produce 0, it breaks. The formula requires you to divide by a number that equals 0 when speed equals light speed. Division by 0 doesn't give an answer, it gives infinity or an undefined result. The math isn't saying your clock runs infinitely slow. It's saying this scenario is physically impossible for matter. The equation is drawing a hard line. It works for any speed up to but below light speed for massive objects. It works exactly at light speed for massless particles like photons. It produces nonsense if you try to push a massive object across that line. The math isn't failing, it's being precise. It's telling you that matter and light live on different sides of a mathematical boundary, and the equation behaves differently in each territory. On the matter side, elapsed time approaches 0 but never reaches it. On the light side, elapsed time doesn't merely approach 0, it's set to 0 by the structure of the path itself. And that phrase, the structure of the path, is important. Physicists call it a light-like interval. It's not just about speed, it's about the geometry of the path a photon traces through spacetime. That path has a special geometric property that makes it different from every path a massive particle can take. Think of it this way. Every path through spacetime has a kind of length. For paths that matter can travel, that length is called proper time. It's the time a clock would measure if you carried it along that path. The faster the path through space, the shorter the proper time. Light's path has a proper time of 0. Always, regardless of how far it travels through space. 1 inch, or 1 billion light years, the proper time along the path is 0. That geometric fact is what the slogan is really saying, and the next question is obvious. Why does the geometry work out that way? What makes the path light take so fundamentally different? The answer requires understanding what a light-like interval actually is, and when you see it, the whole picture of space-time clicks into place in a way that changes how you think about the universe. People picture the speed of light as a finish line, a number you're racing toward. Get close enough, and you can almost touch it. That picture is wrong, and the reason it's wrong reveals something profound about the structure of the universe. The speed of light isn't a destination. It's a boundary between two different kinds of existence. On one side of that boundary, everything with mass, protons, electrons, atoms, baseballs, planets, people, spaceships. All of it. Matter can move at any speed from 0 up to just below light speed. It can be accelerated or decelerated. It can be assigned a rest frame. It has a rest mass, a real measurable quantity that exists even when the object is standing still. On the other side of that boundary, massless particles, photons, gluons, the particles that carry gravity in quantum theories. These particles always move at exactly light speed. Always. In any frame, they can never slow down and they can never speed up. They exist only in motion. The boundary between these two regions isn't like a speed limit sign you could ignore if you were brave enough. It's written into the mathematics so deeply that crossing it is geometrically impossible. Here's why. To accelerate a massive object, you need energy. The more energy you pump in, the faster it goes. But as the object approaches light speed, something changes. The energy you add stops going entirely into making it faster. More and more of it goes into increasing the object's effective mass, its resistance to further acceleration. As speed approaches light speed, the amount of energy required to keep accelerating grows without limit. Getting to exactly light speed would require infinite energy. There's no amount of fuel that gets you there. The universe isn't just saying the speed limit is very high, it's saying matter can't cross that line, because the cost is infinite. The wall doesn't get harder to climb, the wall becomes infinite before you reach the top. Light doesn't cross the boundary either, it exists on the other side of it. It didn't start below light speed and accelerate up. A photon is born moving at light speed. It doesn't have the option to slow down. It's a different kind of particle in a different geometric territory. So, what separates these two territories? The precise answer involves the geometry of space-time, specifically something called the space-time interval. The interval between two events, any 2 points in space and time, can be one of three types. Time-like, events close enough in space and far enough apart in time that a massive object could travel between them. A person or a spaceship could get from one to the other. Space-like, events so far apart in space that even light can't bridge the gap in the available time. Nothing from one event can reach the other. Light-like, events that sit exactly on the boundary. A photon could connect them, traveling at exactly light speed. The interval between these events is 0. That 0 interval is the geometric signature of light's path. And understanding it means understanding why the slogan, "Light doesn't experience time," is pointing imprecisely but genuinely at a real geometric fact. Physicists use a word you don't hear outside their world: proper time. Proper time is the time measured by a clock that travels with an object. Wherever the object goes, whatever speed it moves at, the clock moves with it and measures elapsed time from inside that object's experience. Your heartbeat runs on proper time. So does every atom in your body. Proper time is personal. It belongs to the object, to its specific path through space-time. Every path through space-time accumulates proper time as it goes. A person who sits in a chair for 1 hour accumulates 1 hour of proper time. A particle fired through an accelerator at 90% of light speed accumulates less proper time over the same trip, because its path is moving fast through space and slowly through time. A faster path through space means a shorter path through time. This is the deep geometric truth behind time dilation. The clock doesn't actually run slow in any broken sense. It's accumulating proper time along a path that moves differently through the 4 dimensions of space-time. Different paths, different lengths, different amounts of accumulated proper time. Now trace the path a photon takes. A photon is emitted from a light bulb. It crosses a room. It hits a wall. In the room's frame, the trip takes a few billionths of a second. In the photon's frame, There is no photon's frame in the ordinary sense, but the geometric question still has an answer. The proper time along the light-like path is 0. Every single light-like path has 0 elapsed proper time. A photon crossing a room, 0. A photon traveling from the Andromeda galaxy 2.5 million light-years away to your eye, also 0. The distance doesn't matter. The geometry gives the same result. Emission and absorption sit at 0 proper time separation along the photon's path. The start of the journey and the end of the journey are connected by a geometric interval of 0. That's the fact the slogan is gesturing at. The slogan says it like the photon has a subjective experience of frozen time. The geometric version says the path itself has 0 length in the time dimension. The distinction matters because one invites you to imagine a photon with a clock reading 0. The other tells you there's no clock to read. The concept doesn't apply. Light's path is a different geometric type from the path any clock-carrying object can take. Here's a comparison that might help. Think of a shadow cast by a fast-moving flashlight. The shadow can move across a wall faster than light, but the shadow doesn't carry energy, information, or anything real from one place to another. It's a pattern, not an object. You can't put a clock on a shadow. Asking what time the shadow experiences is a category mistake. Asking what time a photon experiences is close to the same type of mistake. The geometry doesn't assign it. The photon isn't frozen at 0, it's on a path for which the time coordinate simply doesn't function the way it does for massive objects. That's the real answer. Precise, strange, and much more interesting than the slogan. But here's what this leads to. If light occupies a geometric category that matter can never reach, what stops matter from crossing over? Why can't you just keep accelerating until you join light at that light-like boundary? The answer involves a wall made of energy, and it grows without limit. The wall exists, it's real, and it gets bigger the closer you get. Here's how to picture it. You push a car, it starts moving, you keep pushing, it speeds up. The harder you push, the faster it goes. Simple, Newtonian. That's how physics felt for most of human history. Now imagine instead of a car, you're pushing a particle inside an accelerator. You're using magnetic fields to push it, the most powerful push possible. At low speeds, everything works like the car. More energy goes in, more speed comes out. But as the particle climbs past 10% of light speed, something changes. The energy isn't converting cleanly into speed anymore. Some of it is going somewhere else. The particle is getting harder to push, not because of friction, but because its effective resistance to acceleration is growing. Physicists call this relativistic mass. The faster the particle moves, the heavier it behaves, and the more energy you need to push it even a little faster. At 90% of light speed, the particle resists acceleration as if it weighs more than twice its rest mass. At 99%, more than 7 times. At 99.9%, more than 22 times. The numbers climb steeply and without ceiling. To accelerate even one electron all the way to exactly light speed, you would need infinite energy. The most powerful particle accelerator ever built couldn't do it. The entire energy output of the sun for its entire lifetime couldn't do it. There isn't enough energy in the observable universe to push one electron with mass all the way to that limit. The wall isn't a speed limit. It's a mathematical asymptote, an approach that never arrives. This is why the common phrase, "if you traveled at light speed," is problematic. It's fine as a thought experiment tool, pushing the math toward the limit to see what happens. But as a physical plan, it's meaningless for anything with mass. You can't just build a bigger engine. And here's the irony. Light doesn't need energy to reach light speed. It starts there. A photon is born at light speed. It never accelerated through the range of lower speeds. It never passed through the territory matter lives in. It emerged directly into a different category. Matter approaches the light speed boundary from one side, gets asymptotically close, and can never cross. Light exists on the other side, entirely. The two territories are separated not by a gap, but by a geometric discontinuity that the laws of physics enforce. Absolutely. Particle accelerators prove this daily. The most powerful ones on Earth can push protons to 99.9999% of light speed, blisteringly fast. Each additional 9 after the decimal costs exponentially more energy to achieve. Scientists measured every single decimal place of speed gain, and every single measurement matched Einstein's equations exactly. The energy wall is not just theoretical, it has been measured, mapped, and confirmed to extraordinary precision. So matter is locked out. It can approach the boundary, but it cannot cross it. What exists beyond that boundary? What does it mean for a photon to travel through space-time without accumulating proper time? The answer involves how the universe encodes cause and effect. It involves the architecture of reality itself, and it starts with a question so basic most people never think to ask it. What does the journey actually look like from inside a spacecraft approaching that limit? The phrase, frozen time, sounds like a photon riding through a universe stuck on pause. Everything locked still, light zipping through statues of galaxies. That picture is vivid and entirely wrong. Here's what the math actually says. The proper time along a light-like path is 0. That's the geometric fact. But 0 proper time doesn't mean the universe is frozen. It means the concept of elapsed time, as measured by a clock traveling with the object, doesn't apply to that path. Here's an analogy. Imagine you're drawing a line on a map. Every line has a length. A line pointing north has length. A line pointing east has length. But now imagine a line pointing in the time direction only, moving forward through hours but not covering any space. It has a kind of length measured in time, not distance. In space-time geometry, there's a special case. A light-like path is one where the spatial distance covered and the temporal distance covered balance out in an exact way. Specifically, the spatial distance equals the speed of light multiplied by the time interval. When this happens, the interval between the start and end of the path, calculated using the geometry of space-time, comes out to exactly 0. 0 interval, 0 proper time. That 0 is a geometric property of the path itself. It's saying, the start of this path and the end of this path are connected in a specific geometric relationship. It's a statement about the shape of the universe's fabric, about how those two events relate within space-time. It's not a statement about experience. It's not saying the photon feels no time. It's saying the path has a particular geometric signature. Think of it this way. A circle drawn on paper has a circumference. The formula for circumference involves pi. Nowhere in that formula is there a section for the circle's feelings. The circle doesn't experience being circular. The formula is a geometric fact about shape. Saying 0 proper time elapses along a light-like path is like saying the circumference formula applies to circles. It's a statement about geometry. The photon doesn't experience it. The path just has that property. Now here's where it gets meaningful for the larger picture. That geometric property, the 0 interval, is what defines the causal boundary of the universe. Events connected by light-like paths are on the exact edge of cause and effect. Events inside that boundary, connected by time-like paths, can influence each other through slower-than-light signals. Events outside that boundary, connected by space-like intervals, cannot influence each other at all within ordinary physics. Light marks the edge of causality, the point where one event can just barely reach another. That role, marking the boundary of cause and effect, is far more important than the slogan about frozen time. Light doesn't just happen to travel fast. It defines the speed at which information and influence move through the universe. It draws the map of what can affect what. The 0 proper time result is the mathematical signature of that role. It's geometry telling you, this path is on the boundary. And the next question is the one that turns this from abstract to visceral. If a massive traveler could ride arbitrarily close to that boundary, what would they actually see? Two categories, two completely different kinds of things, and the universe treats them differently at the most fundamental level. Everything with mass belongs to category 1: protons, electrons, quarks, atoms, molecules, rocks, water, air, stars, planets, you. All of it is built from particles that have a rest mass, a measurable quantity of energy locked inside them, even when they're standing still. That energy, described by Einstein's most famous equation, is real and physical. Particles with mass can move at any speed from 0 up to just below light speed. They can accelerate, decelerate, stop. They can be held in your hand. They carry clocks that accumulate proper time. They exist inside valid reference frames, where they sit at rest. Everything without mass belongs to category 2. Photons, the particles of light, and all other electromagnetic waves. Also gluons, which carry the strong nuclear force. Possibly gravitons, the theoretical carriers of gravity, though those haven't been directly detected. Particles without mass always move at exactly light speed. They cannot slow down. They cannot stop. They have no rest frame. They accumulate no proper time along their paths. These two categories never mix. A particle either has rest mass or it doesn't. There's no in between. No particle sits halfway between the two groups. The boundary is absolute, and this boundary shapes everything. The reason matter can't reach light speed isn't just the energy wall, though that wall is real. The deeper reason is that matter belongs to the wrong geometric category. Matter's paths through space-time are time-like. Light's paths are light-like. They're different types of curves through the fabric of space-time, and you can't smoothly transform one into the other. Imagine two roads. One goes uphill through a valley, the other is a flat highway. No matter how fast a car drives on the valley road, it never becomes the flat highway. The roads are different shapes. Speed doesn't change the shape of the path. Similarly, no matter how fast matter moves, it stays on a time-like path. Light stays on a light-like path. The geometry of the path is fixed by whether or not the object has mass. Speed changes how much proper time accumulates along the path. It doesn't change the fundamental type of the path. This means the slogan, while poetic, conflates two different things. Time dilation for matter is a gradual effect. The faster you move, the less proper time accumulates on your path. Approach light speed, and proper time approaches 0. That's a continuous sliding effect within the massive particle category. Photons don't experience the end result of that sliding. They live in a separate category where the sliding scale doesn't apply. They were never on the scale. They don't have 0 proper time because they moved so fast. They have 0 proper time because their geometric path type is inherently different. The slogan blurs that line. It makes light sound like the fastest runner crossing the finish line of time, a runner who took the race so seriously they arrived before time itself could tick. The accurate picture is that light was never in that race. It exists in a different geometry entirely. That difference isn't just philosophical. It has consequences you can see. Physical, visual, astonishing consequences that would hit you in the face if you ever came close to that boundary. Because at near light speed, the universe around you stops looking like itself. The light in front of you bends toward a new color. The stars rearrange. The sky behind you grows dark. Picture yourself in a spacecraft. The engines push you faster. 30% of light speed. 50, 70. The universe outside the window is changing in ways no one who's never studied relativity would expect. And the changes start with color. At low speeds, the stars outside look normal, spread across the dome of the sky, roughly even in all directions, white and faintly blue and faintly red. As your speed climbs, something starts happening ahead of you. The stars in front begin to shift. Their light, arriving at your eyes, is being compressed by your motion toward it. Shorter wavelengths, bluer colors, stars that were white turn electric blue, stars that were faintly yellow go blue-white. The whole region of sky ahead of you brightens. This is called blue shift. When you move toward a light source, the waves bunch up. More wave crests hit your eyes per second. Higher frequency, bluer light. The stars there are doing the opposite. Their light is being stretched by your motion away from them. Longer wavelengths. Redder colors. White stars turn orange. Orange stars turn deep red. Deep red stars fade towards infrared, beyond the range your eyes can detect. The sky behind you is dimming, darkening. At 90% of light speed, the stars behind have mostly shifted into infrared. You can't see them anymore. The rear view is nearly black. The sky in front is almost painfully bright. All the light from ahead is crowding into a smaller and smaller patch of sky. Stars that were spread across a wide arc are being pulled toward a central point directly in front of you, like rain on a car windshield, all streaming toward the center. As you accelerate, that compression of starlight into a forward cone is called relativistic beaming. At 90% of light speed, more than half the visible sky has been squeezed into a cone roughly 30 degrees wide in front of you. The rest of the sky is dark. The universe has changed shape. Stars that were scattered in all directions now appear to crowd forward. The geometry of the sky itself has distorted around your motion. Now imagine holding a clock up to the window and looking at a distant station you're flying past. Their clocks run slower from your perspective because you're moving so fast relative to them. But you also have to account for the signal delay of light traveling between you. When you're flying toward the station, the light carrying the image of their clock has less distance to cover each moment, so images arrive faster than normal, and their clock appears to run faster than expected. When you fly away, the opposite happens, and their clock appears to run slower. The visual experience of time at near light speed is layered and strange. Your own watch is fine, but the universe outside the window has been remapped by your speed. And this is still at 90% of light speed. Still firmly in the territory of massive particles. Still inside the rule that says proper time accumulates. Your clock ticks. Your heart beats. You are genuinely a different geometric category from the photons streaming past your window. But what those photons are doing, what path they're tracing through the fabric of space-time, that's what comes next. And the picture it draws is one of the strangest in all of science. Color is the universe's speedometer. You don't need a dashboard readout to know how fast you're moving through space. You just need to look at the light around you. The color of incoming light tells you everything about your motion relative to its source. Here's how it works. Light travels as a wave. Like waves on water, it has peaks and valleys. The distance between two peaks is the wavelength. The number of peaks that hit your eye per second is the frequency. These two things together determine color. Short wavelength, high frequency, blue. Long wavelength, low frequency, red. Everything else sits somewhere between. Now imagine you're moving toward a light source. Each peak of the wave has slightly less distance to travel to reach you than the one before it. They arrive bunched together. More peaks per second, higher frequency. The light shifts toward blue, move away from a source, and each peak has slightly more distance to cover. They spread out. Fewer per second, lower frequency. The light shifts toward red. This happens with sound, too. A siren on an approaching ambulance sounds higher pitched than when it's moving away. Same principle. The wave is compressed on the approach and stretched on the retreat. For sound, that's called the Doppler effect. For light, it still is, but at speeds near light speed, relativity adds an extra layer on top. At low speeds, the color shift is tiny. A car driving toward you shifts your headlights by an amount too small to see. But as speed climbs toward a meaningful fraction of light speed, the shift becomes dramatic. At 50% of light speed approaching a star, That star shifts significantly toward blue. A star that appeared yellow-white now burns a hard blue. At 90%, stars ahead have shifted so far into blue and ultraviolet that some of their light has moved beyond what the human eye can even detect. The sky ahead glows in frequencies that human eyes weren't built for. Behind you, the same stars that used to glow yellow and orange have drifted deep into red, then infrared, then radio waves. Wavelengths so long your eyes register nothing. The background of the universe fades into invisible. Here's the part that strikes hardest. The cosmic microwave background radiation, a faint glow of light left over from the early universe that fills all of space in every direction, would shift dramatically too. Ahead of you, that background shifts from microwave frequencies into visible light, flooding the forward sky with a faint but real glow from the birth of the universe itself. Behind you, it stretches into radio waves and vanishes. You would be flying into an increasingly bright forward cone of compressed ancient light, while behind you, the universe went dark. And this color shift isn't just visual poetry. It carries real energy consequences. Blue shifted light hits you with more energy per photon. A spacecraft at 90% of light speed heading toward a star would absorb radiation hitting its forward face at dramatically higher energies than the star would normally emit at that distance. Engineering a spacecraft that could survive that bombardment is an extraordinary problem. The color of light is telling you about relative motion, about the geometry of your path through space-time, and about the real physical consequences of moving through a universe built on those rules. Every photon hitting your face carries information about where it came from, when it left, and how you've been moving. The sky is a map of your velocity, written in color, and those photons, the ones arriving at your face, took paths through space-time that are geometrically different from the path your body takes. Their story is about to get stranger. At 90% of light speed, the sky behind you has gone nearly black. Not dark the way a cloudy night is dark. Dark the way a turned-off television is dark. Absent. The stars are still there, billions of them, but their light has been stretched so far toward long wavelengths that almost none of it remains visible. The photons are still coming. You just can't see them anymore. Your eyes evolved to detect a narrow slice of the electromagnetic spectrum, roughly the range from deep violet to deep red. That window represents the wavelengths most abundant in sunlight, which makes sense because your eyes developed under a sun. But that window is a tiny fraction of the full electromagnetic spectrum, which runs from gamma rays at one end to radio waves at the other, spanning a range of frequency more than 10 billion times wider than the strip you can see. At near light speed, the stars behind you emit light that has been stretched into the radio portion of that spectrum. Those waves are still real, they carry real energy, but they're invisible to human eyes. The universe behind you is broadcasting in a frequency you can't receive. Meanwhile, the sky ahead is doing the opposite. Stars not only shift blue, they shift into ultraviolet and beyond. Ultraviolet is also invisible to human eyes. So at extreme speeds, the star directly ahead of you might actually be invisible too, pouring all its energy into frequencies above what you can detect, while the circle around it blazes blue-white with stars that have shifted into the visible range. The full picture. You're flying through a tunnel of visible light, a bright, compressed ring or cap of blue-white stars ahead, a ring of fading red at the boundary behind, blackness in the rear. The geometry of the visible sky has collapsed inward around your direction of motion. Physicists call the forward concentration of light relativistic beaming, or the headlight effect. A moving light source emits its light preferentially in the forward direction from the perspective of a stationary observer. The reverse is true for an observer riding the source. Incoming light from all around gets beamed into the forward hemisphere. At 99% of light speed, more than 99% of all the light in the universe appears to come from a forward cone less than 8 degrees wide. Imagine the entire sky compressed into a circle smaller than your fist held at arm's length. Everywhere else, darkness. That's not a metaphor. That's the geometric consequence of how light waves and relativistic motion interact. Scientists have modeled these visual effects precisely and confirmed them through calculations that match the underlying physics. Now add the time dilation. You're moving so fast that your clock runs at a fraction of the rate of clocks on Earth. For every year you experience inside the spacecraft, years or decades pass outside. The stars ahead are not just visually compressed, you're moving through the universe faster in coordinate time than your own clock reads. And all of this, the compression, the darkness, the time gap, all of it is still on the massive particle side of the boundary. You're still accumulating proper time, your clock still ticks, your path through space-time is still time-like. The photons flying past your window, the ones shifting from red to blue and back again as you pass them, those are on the other side of the line. Their paths are light-like, zero proper time. The darkness behind you is a vivid reminder of just how different those two types of paths are. Here is the strangest comfort in all of physics. No matter how fast you fly, no matter how extreme the time dilation, no matter how many years pass outside your window, your own clock always reads normally to you. Always. 1 second feels like 1 second. Your coffee cools at the normal rate. Your heartbeat is the same pace. Your thoughts move at their usual speed. Your clock on the wall ticks once per second, every second, without any drama. The person on Earth watching you through a telescope might see your clock running at a fraction of normal speed. Depending on how fast you're moving, they might measure 10 years passing outside while your clock shows only 1. But inside the spacecraft, you have no sensation of anything unusual. Nothing slows down. Nothing speeds up. You feel normal because you are normal, inside your own frame. This is one of the hardest ideas in all of relativity to sit with, because the intuitive response is, if my clock is running slow, I must feel it somehow. If a year passes outside while I experience a month, shouldn't something feel compressed? Shouldn't I feel like I'm watching the universe on fast forward? No. And the reason is precise. Your clock isn't malfunctioning. It isn't running slow due to some mechanical problem. It's accumulating proper time along your specific path through space-time. That proper time is genuinely shorter than the coordinate time measured by Earth observers. You're not experiencing a delayed version of Earth's time. You're experiencing a different quantity of time entirely, the time along your path. Your body, your thoughts, your watch, every physical process you experience runs at its natural rate relative to your own path. There's nothing to feel slow or fast, because your entire frame is consistent with itself. Think of it this way. You can't feel that you're on a spinning planet. Earth rotates at around 1,000 miles per hour at the equator. You don't feel that spin because everything around you, the air, the ground, the coffee in your cup, all spins with you. There's no internal sensation that tells you you're spinning. You only find out by looking at the stars long enough to watch them arc across the sky. Time dilation works similarly. Your entire local physics, every atom, every electron, every chemical reaction in your brain, all of it runs at the same pace relative to your frame. The only evidence of anything unusual comes when you compare with someone outside that frame. This principle is called the equivalence of inertial frames, and it's the bedrock of special relativity. Every smoothly moving frame is physics equivalent. No experiment you can run inside a smoothly moving spacecraft tells you how fast you're going. You need an outside reference. So the traveler who crosses the galaxy at near light speed and returns to find Earth 1,000 years older has done nothing unusual from inside their own frame. They lived a normal life at a normal pace. They just accumulated less proper time along their path. Two people, same starting point, same ending point, different amounts have passed between them. Your clock is always right. The universe just has room for many different clocks to all be right at the same time. Which raises a genuinely unsettling question. If two observers can disagree on how much time has passed, What else can they disagree on? What happens to the concept of now at near light speed? This is the experiment that proves everything. Two identical twins, same age, same height, same birthday. One stays on Earth. One boards a spacecraft and flies to a nearby star at 90% of light speed, then turns around and comes back. When the traveling twin returns, they are younger, measurably, physically, biologically younger. Their cells have divided fewer times. Their telomeres are longer. Their hair has fewer grey strands. Less time genuinely passed for them. This is called the twin paradox. It gets that name because it sounds contradictory. If motion is relative, if the spacecraft twin sees Earth moving away just as much as Earth sees the spacecraft moving away, why does only one twin age less? Why isn't the effect symmetric? The answer is the turn. The spacecraft twin had to change direction to come back. They had to decelerate, stop, and accelerate again in the opposite direction. That change of motion breaks the symmetry. The Earth twin stayed in a single inertial frame the whole time. The spacecraft twin switched frames. That switch is physically real and measurable. The spacecraft twin genuinely experienced a different geometric path through space-time, one with less accumulated proper time. The turn is what makes the difference. The asymmetry is built into the geometry of the paths, not into some arbitrary choice of who's moving. Physicists haven't literally run this experiment with twins, but they've run the equivalent with particles. Muons in storage rings at particle accelerators move in circles at close to light speed. They survive far longer than muons at rest because their clocks run slow. They make the round trip, returning to their starting point having aged less than their stationary counterparts. The experiment has also been run with atomic clocks on aircraft, as mentioned in an earlier chapter. The clocks that flew came back slightly behind. The amount of lag matched the predictions with extraordinary accuracy. Here's the human scale of the effect. A spacecraft traveling at 90% of light speed takes about 9 years in Earth time to reach the nearest star system beyond our Sun, roughly 4 light-years away. The traveling twin experiences about 4 years. They return after 18 Earth years, having aged only 8. At 99% of light speed, the ratio becomes more extreme. A journey that takes 100 Earth years might correspond to only about 14 years on the ship. At 99.9%, the compression is even more dramatic. This is real. It's confirmed. It happens. The universe genuinely allows two paths between the same two events to have different lengths in time. This is the full consequence of what began in Chapter 2, with 2 people and 2 watches. The effect scales all the way up to biology. A human being can age less than their twin by traveling fast and coming back. The universe permits it, and the entire effect, from beginning to end, involves massive particles, people, ships, clocks, muons, all of it in the time-like category, all of it accumulating proper time, just different amounts. Now scale that up. Imagine traveling so fast that your proper time approaches 0 per journey. Imagine a path along which so little proper time accumulates that the gap between 2 events compresses toward nothing. You're approaching the light-like category. You're approaching the geometry that light lives in permanently. And the closer you get to that boundary, the more the next question takes over. What does it mean that light sits exactly at that edge? About 17 miles outside Geneva, Switzerland, buried in a circular tunnel, 100 meters underground, sits the largest machine human beings have ever built. The Large Hadron Collider, a ring of superconducting magnets, 17 miles in circumference, powerful enough to bend the path of protons traveling at 99.9999% of the speed of light. Every second it operates, the relativity in this script is being tested and confirmed in real time. Protons are fed into the ring and accelerated by powerful electric fields. Magnets steer them around the loop. They gain speed, then more speed. The magnetic fields grow stronger to keep the increasingly fast protons on track, because as speed increases, the protons behave as though they're heavier, curving less sharply in any given magnetic field. Engineers have to compensate precisely using the exact equations Einstein derived. At top speed, a proton in the collider is moving so close to light speed that from our perspective in the laboratory, its internal clock is running at a tiny fraction of our rate. If that proton carried a watch, our clocks would tick roughly 7,000 times for every one tick of the proton's clock. 7,000 to 1. This isn't a calculation on paper, it's a measurable operational fact. The entire timing system of the accelerator depends on accounting for this effect correctly. If engineers didn't apply relativistic corrections, the protons would arrive at the wrong place at the wrong time, beams wouldn't collide, and the machine wouldn't function. Relativity is not a theory sitting on a shelf. It's the engineering manual for the most precise machine on Earth. Now consider unstable particles. When physicists create exotic particles in collisions, those particles have known lifetimes. A certain particle might survive for a few billionths of a second before decaying. At low speeds, you can measure exactly how far it travels before it falls apart. At near light speed, those particles travel much farther than their lifetime would predict if time ran normally. Their clocks are running slow. From their perspective, the same tiny sliver of proper time passes. But from the lab's perspective, far more coordinate time passes, giving them more distance to cover before decay. This has been measured for dozens of different particle types, pions, kaons, muons, and more. Every measurement matches Einstein's predictions. The faster they move, the longer they survive in lab time. The ratio matches the Lorentz factor exactly every time. There is no wiggle room here, no alternative explanation. The particles live longer because time is geometrically different for fast-moving objects. Now here's the escalation. All of this, the protons, the pions, the muons, all of it operates at very close to light speed, but still on the massive side of the boundary. The particles still have rest mass. They still accumulate proper time. Their clocks run slow, but they run. The accelerator can push protons to 7,000 times slower proper time than lab time. At that ratio, you are not far from the light-like boundary, but you're still not there. You're still matter. The gap between 99.9999% of light speed and 100% is infinitely wide in terms of energy cost. The proton will never cross it. What lives on the other side crosses that gap every moment, billions of times per second, in every cubic inch of space. Every time you tap your phone and ask it where you are, a quiet act of relativity happens above your head. Roughly 12,000 miles up, a constellation of satellites circles the Earth. Each satellite carries an atomic clock. That clock is the backbone of the navigation system. Your phone receives signals from several satellites, measures how long each signal took to arrive, and triangulates your position from those travel times. The whole system depends on those clocks being synchronized. If two clocks disagree by 1/1,000,000th of a second, the position error can be nearly 1,000 feet. An error of 1 second would make the system useless for navigation. But those clocks drift, constantly, predictably, due to relativity. Two effects are in play. The first is the one this script has been building toward. Special relativistic time dilation from speed. The satellites orbit at roughly 9,000 miles per hour relative to the ground. That's fast enough that their clocks run slow compared to clocks on Earth. By about 7 microseconds per day, where a microsecond is 1/1,000,000th of a second, 7 microseconds doesn't sound like much. But over a day, an uncorrected 7 microsecond lag translates to a position error of about 1.5 miles. The second effect comes from general relativity, which describes how gravity warps time. Clocks higher up in a gravitational field run faster. The satellites are farther from Earth's center, so they sit in weaker gravity. Their clocks run fast compared to surface clocks by about 45 microseconds per day. The two effects work in opposite directions. Time dilation from speed slows the clocks. Weaker gravity speeds them up. The net result: satellite clocks gain about 38 microseconds per day compared to surface clocks. Engineers correct for this before the satellites even launch. The clocks are deliberately set to run at a slightly slower rate on the ground, so that when they reach orbit and experience weaker gravity, the two effects balance out and the satellite clocks stay synchronized with surface clocks. Without that correction, position errors would accumulate at roughly 7 miles per day. After a week, your phone would think you're on the other side of the city. After a month, it would put you in a different state. Every navigation app on every phone on every continent depends on Einstein's equations for accuracy. Every delivery truck, every commercial aircraft, every ship at sea that uses satellite navigation is flying on Einstein's math. This is the moment where the abstract becomes concrete. The curves of space-time, the dilation of moving clocks, the stretching of time near mass, all of it is real enough that industrial civilization has been quietly engineered around it for decades. And the engineers who built these corrections didn't do so based on theory alone. They tested the predictions, measured the drift, confirmed the numbers, and built the corrections into hardware. It worked. It still works, every day, billions of times a day. Time dilation from speed, time change from gravity, both confirmed, both quantified, both corrected for in a device in your pocket. The same relativity that says light traces a path of 0 proper time through space-time is the same relativity that makes sure your maps are accurate. It's one coherent framework, tested from the surface of the Earth to the edge of the observable universe. And at the edge of that framework sits a question that goes deeper than clocks and satellites. What does it mean that light defines the boundary of what can influence what? What is the structure of cause and effect at the most fundamental level? Cause and effect sound simple. You knock over a glass, it falls. The knock came first, the fall came second. One caused the other, but that simple picture has a hidden requirement. Information about the knock had to travel to the glass before the glass could fall. If nothing can carry that information faster than light, then cause and effect are bounded by light speed. Events can only influence other events they can reach in time. This is the causal structure of the universe. And light draws its map. Picture every event in space-time as a point, a moment in time at a specific location in space. From that point, light spreads outward in all directions, forming an expanding sphere. After 1 second, that sphere has a radius of 186,000 miles. After 1 year, a radius of 1 light year, the surface of that expanding sphere is called the light cone. It's drawn as a cone because when you flatten space-time down to 2 dimensions for a diagram, time going up and 1 dimension of space going sideways, the expanding sphere of light looks like a cone opening upward from the event. Any event inside that cone, any location reachable within the time available at speeds up to light speed, can be causally influenced by the original event. Information can travel there, forces can reach there, a signal can connect them. Any event outside the cone is causally disconnected from the original event. The distance is too large and the time too short. Even light can't bridge the gap. Nothing from the original event can reach those points. Nothing from those points can reach the original event. Light sits on the exact boundary of that cone. A photon emitted from an event travels exactly along the surface of the light cone. It's the fastest possible messenger, and it defines the edge of what can communicate with what. This means light doesn't just travel through space-time. It defines the causal architecture of space-time. It draws the boundary between the connected universe and the unreachable universe. Every event in the history of the cosmos has a light cone. The overlapping and nested structure of all those cones is what gives the universe its causal coherence. Cause before effect, effect after cause. That ordering holds because information can't travel faster than light. The light cone enforces the sequence. If something could travel faster than light, it could, in certain configurations, arrive at a destination before it left its origin. Cause and effect would reverse. An effect could precede its cause. The result would be a universe where the sequence of events becomes ambiguous, a logical catastrophe that physicists call a causality violation. No such faster-than-light signal has ever been detected. Every experiment, every observation, every precision test has confirmed that the causal boundary holds. Light speed is the wall between ordered cause and effect and a universe that makes no sense. That's why the speed of light is not just fast, it's structural. It's the speed at which the universe communicates with itself. It's the rate at which one part of reality can affect another. Every force, every signal, every influence, every consequence propagates at light speed or slower, and a photon, traveling along the surface of the light cone, traces that boundary precisely. Zero proper time, the edge of cause and effect, the fastest possible messenger carrying the universe's rules from one event to another. That role is what makes light central to physics. Something even stranger is coming. The universe doesn't measure distance the way you do. You measure distance with rulers. The length of a path through space, 3 feet across a room, 2,800 miles from New York to Los Angeles, 93 million miles to the sun. The universe keeps track of something else, something that mixes space and time together. Physicists call it the space-time interval. Here's how it works. Between any two events in the universe, any 2 points in space and time, you can calculate an interval. The interval uses the distance in space between the events and the separation in time between them. You combine them with a specific formula. The formula is designed so that every observer in any reference frame, regardless of how fast they're moving, calculates the same interval for the same pair of events, unlike distances in space, which change depending on how fast you're moving. And unlike time gaps, which also change, the space-time interval stays fixed. It's the one quantity that relativity preserves. This makes it the universe's true ruler, the measurement that doesn't depend on who's measuring. Now, the interval comes out to one of 3 types. If the interval is positive, meaning time-dominated, the events are in a time-like relationship. A massive particle can travel between them. Cause and effect can connect them. Proper time accumulates between them. If the interval is negative, meaning space-dominated, the events are in a space-like relationship. They're too far apart in space relative to their time separation for even light to connect them. Cause and effect cannot link them directly. If the interval is exactly 0, the events are in a light-like relationship. A photon can connect them. They sit precisely on each other's light cone. This is the boundary case. Every photon's path through space-time is a string of light-like intervals. Every step of the journey connects 2 events with 0 space-time interval. The beginning of the photon's existence and the end of its existence are separated by 0 interval, no matter how much space or time lies between them in any particular observer's frame. That 0 interval is the precise geometric statement behind the slogan. The photon's path has 0 length in the universe's true ruler. Emission and absorption are at 0 interval. The path from a star 400 light-years away to your eye tonight has 0 space-time length. This is genuinely strange. In ordinary space, a longer physical journey means a longer distance. In space-time, a light-like journey spanning billions of light-years has 0 interval. The universe's ruler returns 0. Now imagine 2 events far apart in space, connected by a light-like interval. Nothing physically connects them except a photon. The photon is the thread holding those 2 events together, and the thread has 0 length in the universe's own measurement system. That's not the photon having a strange experience. It's the universe telling you something deep about the geometry of the space-time fabric. 2 events, separated by cosmic distances in our frame, are in some geometric sense immediate to each other, 0 apart, connected. And this geometric fact runs deeper than any slogan. It goes all the way down to the structure of space-time itself, a structure that physicists still don't fully understand at the smallest scales. But that's not the most surprising thing that follows from all this. The most surprising thing is what happens when you try to chase light. Imagine you're in the fastest spacecraft ever built. You've pushed it to 99% of light speed. You fire a flashlight forward. A beam of light shoots out ahead of you. Common sense says you're already moving at 99% of light speed, and the light moves at 100%. So the light should be pulling away from you at 1% of light speed, a tiny gap, barely escaping. Measure it. The beam is moving away from you at 186,000 miles per second. The full number. Not 1%, 100%, the complete, undiminished speed of light. This is the moment where relativity stops being an abstract theory and becomes visceral. You are moving at 99% of light speed. The light is pulling away at 100% of light speed. The gap between you is growing at 100% of light speed from your perspective, even though you're already almost at that speed yourself. How is that possible? Because the way velocities combine at high speeds is different from how they combine at low speeds. The everyday rule says speeds add directly. Your speed plus the speed of the thrown ball equals the ball's speed to an outside observer. That rule works perfectly below, say, 10% of light speed. The error is negligible. At high speeds, a different formula takes over, the relativistic velocity addition formula. It ensures that no combination of two speeds below light speed can ever produce a result at or above light speed. You can add 99% of light speed to 99% of light speed, and the result is not 198%. It comes out to about 99.99%. The formula builds in a ceiling. Speeds don't simply add anymore. They blend in a way that always keeps the result below light speed for massive objects. And light itself always comes out at exactly light speed, regardless of the motion of the source or the observer. Chase it at 99%, and it still reads as 186,000 miles per second. Chase it at 99.9%, and you get the same number. The beam never slows down relative to you. This was the scenario that young Einstein turned over in his mind in the years before 1905. What would it look like to ride alongside a beam of light? Could you pace it? Could you sit next to it as it moved, watching the wave frozen beside you? He concluded you couldn't. Maxwell's equations, the equations describing electromagnetic waves, stopped making sense if you assumed you could freeze light in your frame. The wave would collapse. The physics would break. The only consistent answer was that light always moves at the same speed for all observers, and that space and time had to adjust to make it so. That thought, carried to its conclusion, produced special relativity, and what it means for the chase is simple and absolute. You can never catch light. You can never sit beside a beam and watch it. You can never reduce the gap. The gap is always the full speed of light. Always, every time you measure it, no matter how fast you move. Light isn't running away from you because it's fast. It's running away from you because it's a different kind of thing in the universe. The rules of motion that apply to you simply don't apply to it. And if that seems like the strangest consequence of these rules, one more discovery is waiting. One that takes everything apart at the foundations. Two events happen at the same time. Seems simple, at rest relative to each other. Two people agree. Event A and Event B happen simultaneously. They saw the flashes at the same moment. It's settled. Now put one of them on a fast-moving train. This experiment is one of Einstein's original thought experiments, and it's the one that most quietly dismantles your assumptions about the universe. Picture a train moving at high speed. An observer stands in the exact center of one of the cars. Two lightning bolts strike the front and back of the train simultaneously, according to an observer standing on the platform outside. Both observers see the flashes. the platform observer, standing equidistant from both strike points and not moving, receives both light signals at the same moment and concludes, the strikes were simultaneous. The observer on the train is in the center of the car, but the train is moving. The train is rushing toward the front strike and away from the back strike. Light from the front reaches the train observer slightly sooner, because the train observer is moving toward it. Light from the back reaches them slightly later, because they're moving away from it. The train observer receives the front flash first and concludes, the front strike happened before the back strike. Same two events, different verdicts. And here's the critical part. Both observers are correct within their own reference frames. There's no fact of the matter that settles it. The sequence of the two events depends on the observer's motion. Simultaneity isn't a universal property of events. It's a relationship between events and observers. Events that are simultaneous in one frame are not simultaneous in another. The ordering of events that are space-like separated, events too far apart for light to connect in the available time, can actually reverse depending on the observer's velocity. This isn't a weird edge case. It's a fundamental feature of space-time. Time is not a universal backdrop ticking the same for everyone. Every observer carries their own slice of time, their own definition of now, their own ordering of events. For events connected by light or slower signals, time-like events, the ordering is preserved. Cause still precedes effect for every observer. That causal ordering holds because those events are connected by something real crossing the space between them. For events in space-like separation, no signal can connect them. No cause and effect links them, and the ordering of such events is genuinely observer-dependent. In that technical sense, there's no universal now across space. That conclusion sat at the heart of Einstein's 1905 paper. Space and time are not separate fixed stages. They're a single four-dimensional fabric, space-time, and different observers slice through that fabric at different angles, depending on their velocity. Each observer's now is a different slice, and light, traveling at the exact speed that defines the boundary of cause and effect, sits at the seam between the ordered universe and the frame-dependent one. The deeper the physics goes, the more central light becomes. The speed limit, the causal boundary, the ruler of proper time, the divider between what can and can't be simultaneous. And underneath all of it, a question physicists haven't yet fully answered. You've been picturing space as a stage. 3 dimensions, room to move, things happening in it, and time as a clock ticking above the stage, marking when each event occurs. Einstein replaced that picture with something more accurate and far stranger. Space and time are one thing. Space-time, 4 dimensions woven together, 3 of space and 1 of time, forming a single geometric fabric. Objects don't move through space with time ticking in the background. They trace paths through space-time. Their entire journey, from birth to death, is a single curve in 4 dimensions, called a world line. Your world line starts when you were born and ends when you die. Every moment of your life, every position you've ever occupied, is a point on that world line. It stretches through 4 dimensions. Now here's what the theory says about that fabric. Mass warps it. A massive object like the Earth creates a curve in the space-time fabric around it. Other objects moving nearby follow that curve. What we call gravity is the result of objects following the straightest possible paths through curved space-time. This is general relativity, the extension of special relativity that Einstein published 10 years later in 1915. It added gravity to the picture by describing space-time as a flexible geometric structure that bends in response to mass and energy. Light follows that curvature too. A beam of light passing near a massive object bends, not because a force pulls the photon sideways, but because the photon follows the straightest possible path through curved space-time. And near a mass, the straightest path is curved. This was one of Einstein's most dramatic predictions. In 1919, a British expedition observed stars during a solar eclipse. Stars whose light passed close to the Sun appeared shifted in position, exactly the amount Einstein predicted. The space-time fabric was bending light. That observation made Einstein famous worldwide overnight. But the structure of space-time itself remains one of the deepest open problems in physics. General relativity describes it beautifully at large scales. Quantum mechanics describes particles and forces at tiny scales with extraordinary precision. These two frameworks are both confirmed by experiment, and they are currently incompatible with each other at the mathematical level. Where both are relevant at once, for instance at the center of a black hole, or in the earliest instant of the Big Bang, the equations break down. Neither theory gives a clean answer. Physicists have been working on a unified theory for roughly a century. String theory, loop quantum gravity, and other approaches have each made partial progress. None has produced a complete, tested framework. What this means for light is humbling. The statement that light traces paths of zero proper time through spacetime is a precise statement within the tested framework of special and general relativity. It's confirmed. It's structural. But whether space-time itself is truly continuous, whether it has a granular structure at the very smallest scales, whether time is a fundamental feature of reality or an emergent one, those questions remain genuinely open. The picture you've been building through this script, accurate and tested as it is, may be a large-scale approximation of something deeper that no human has seen yet. Light, which defines the causal structure of everything we know, may sit at the boundary of what the next theory will explain. You've heard the popular version. Light doesn't experience time. Photon leaves a star, arrives at your eye, and for the light, the journey was instantaneous. It's a great hook. It grabs attention. It suggests something miraculous about the nature of light, and it quietly teaches you the wrong lesson. The popular version pictures a conscious photon riding through a frozen universe, a particle with a perspective, watching everything locked in pause while it zips across the cosmos. The slogan invites you to imagine climbing into the photon's seat and looking out. Physicists can't do that. The theory doesn't allow it. A photon has no seat, no valid rest frame, no perspective in the sense of an inertial observer carrying a clock and watching events unfold. The machinery the slogan uses to make the idea feel intuitive is the same machinery the physics explicitly prohibits. The precise version says this: the space-time interval along a light-like path is zero. Proper time is undefined for a massless particle. The geometric path light takes through space-time connects emission and absorption events with a zero interval, regardless of how large the spatial distance between them is, in any given frame. The precise version is stranger than the popular one, and more interesting. It's not saying a photon has a funny experience of time. It's saying time, as measured by proper clocks, doesn't apply to light's path the way it applies to yours. The concept transfers over in a degenerate form. It comes out zero. But that zero is a geometric fact about the path type, not a report from inside the photon. The difference matters because the popular version teaches something false. It teaches that if you were moving as fast as light, you'd experience frozen time. You'd be conscious but surrounded by a paused universe. That's not what the physics says. The physics says you can't move as fast as light if you have mass. And if you approach that speed, your proper time doesn't freeze. It accumulates more slowly, but it accumulates. You keep experiencing things normally from inside your frame. The freeze only shows up as a limit. Push the math toward light speed for a massive particle, and proper time approaches zero asymptotically. It never actually reaches zero for anything with mass. The popular version also makes people think of light as the ultimate traveler, faster than everything. So fast, it transcends time. The precise version makes light something more interesting, a different category of physical entity, a geometric type of path. the thing that defines the causal boundary of the universe, the measurement against which space-time's own ruler is calibrated. That's not a traveler transcending time. That's light being fundamental to the structure of reality. Scientists who popularize physics face a real tension. The precise version is harder to explain. The slogan is faster, catchier, and gets people interested. Those are genuine goods. But a slogan that teaches a false picture can become the thing people defend when the real explanation comes along. It can make the truth feel like a disappointment rather than a deeper mystery. The truth here is deeper. Light isn't a fast traveler. It's a geometric boundary, and every experiment, every satellite, every accelerator, every atomic clock confirms that the universe is built around that boundary with extraordinary precision. 13.8 billion years ago, the universe began. Hot, dense, smaller than a single atom, then expanding rapidly in every direction at once. In the first fraction of a second, the universe was so hot that no stable particles could hold together. Everything was a dense plasma of energy and particles in constant collision. Photons existed, but they couldn't travel far. The plasma was so thick with charged particles that a photon would immediately scatter off something and change direction. The universe was opaque. Then, about 380,000 years after the Big Bang, something changed. The universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the plasma was gone. The universe became transparent, and all those photons that had been bouncing around, trapped in the plasma, were released. They streamed outward in every direction, freely, for the first time. We can still detect those photons today. They've been traveling for 13.8 billion years. They fill the sky in every direction, invisible to the naked eye, but detectable with the right instruments. Scientists call this the cosmic microwave background radiation. And here's what those photons carry, in a very precise sense. They are a snapshot of the universe from 380,000 years after the Big Bang. The pattern of tiny temperature variations across the sky, some spots slightly warmer, some slightly cooler, maps the density fluctuations of that ancient plasma. Those fluctuations later grew into galaxies, galaxy clusters, and the large-scale structure of the universe we see today. Now apply what you've learned. Those photons have been traveling for 13.8 billion years in our frame. In that same frame, they've covered enormous distances, billions of light years. Along their own path, zero proper time has elapsed. The moment of their release and the moment your detector absorbs them are connected by a zero space-time interval. In the universe's geometric measurement, those two events are immediate. What does that mean? It means the photon arriving at a detector today is, in a geometric sense, still the same event as its release 380,000 years after the Big Bang. The path between them has zero length in proper time. This doesn't mean the photon traveled instantly. In our frame, it took billions of years. The zero proper time is a property of the path in space-time, not a claim about the coordinates of our frame. But it does mean something profound. The information carried by that photon about the state of the early universe hasn't aged. It hasn't decayed. It's been propagating along a zero-interval path through space-time. From the geometry's perspective, the early universe and the detector are directly connected by a thread of zero length. Every time an astronomer captures one of those ancient photons, they're doing more than looking at an old signal. They're touching the universe at a moment 13.8 billion years in the past, connected by a geometric thread that the universe's own ruler measures as zero. Light doesn't just travel through the universe, it stitches together moments in its history. Here's where the certainty ends. Time dilation, the constant speed of light, the light-like interval, the causal structure of space-time, GPS corrections, particle lifetimes. All tested, all consistent, all standing on a foundation of experiments so solid that engineers build billion-dollar systems on it. But there's a door at the edge of this picture that nobody has opened yet. Special relativity describes space-time as smooth and continuous, a fabric that can bend and stretch, but at every scale, still a fabric. No gaps, no graininess, just smooth geometry stretching in all directions and at all sizes. Quantum mechanics describes the world at small scales very differently. At the quantum level, physical quantities come in discrete chunks. Energy doesn't flow continuously. It comes in packets, called quanta, the smallest possible unit. You can't have half a quantum. At everyday scales, these two descriptions don't conflict. Special relativity handles the fast-moving, large-scale world. Quantum mechanics handles the tiny world of atoms and particles. Both are tested to extraordinary precision in their own domains. Both work. At certain extreme limits, both apply at once. The interior of a black hole, the first instant of the Big Bang, places where the space-time fabric is so curved or so small that quantum effects can't be ignored. At those points, the two frameworks contradict each other. The math breaks. General relativity predicts things that don't make sense in quantum terms. Quantum mechanics doesn't naturally include gravity. The two best confirmed theories in the history of physics cannot both be right at those extreme scales. Physicists have been working toward a unified theory since the 1920s, a theory that gives quantum mechanics and gravity in one framework. String theory suggests that particles are actually tiny vibrating strings of energy in higher dimensions. Loop quantum gravity suggests space-time itself is woven from discrete quantum loops with no space smaller than the Planck length, roughly 10 to the negative 35th meters across. Other approaches exist. None has been confirmed experimentally. None has produced a prediction that could clearly distinguish it from the others and be tested. What does this mean for light and time? In all the tested physics, the picture is clear. Light traces light-like paths with zero proper time. That statement is solid ground. But whether space-time is truly continuous at the smallest scales, whether proper time has meaning below some minimum resolution, whether the zero interval of a light-like path holds all the way down to the quantum foam, or whether something else entirely takes over at those depths, that remains genuinely unknown. The slogan "Light doesn't experience time" points at real physics. The precise version of that physics is confirmed, but the deepest question underneath it, what space-time really is, at its most fundamental level, sits at the frontier of human knowledge, with no confirmed answer yet. The universe has handed physicists their hardest homework, and the subject of the homework is the same thing the script started with, the nature of time itself. Everything in this script has been about light and time and geometry. But it's worth stopping here, before the final chapter, to make it personal. You are subject to every single effect described. Right now, your body is moving through space-time, not through empty space, through space-time. Your path has a shape. Your shape through space-time is a world line that accumulates proper time. Every second you live is a second added to your world line. And that path is affected by your speed and by the gravity you sit inside. You are on the surface of a planet. That planet's mass curves the space-time around you. Your clock runs slightly slower than a clock 100 miles directly above you in orbit because you're deeper in the gravitational well. The difference is tiny, roughly a few microseconds per year, but it's real. Your feet closer to Earth's center than your head actually age very slightly slower than your head. You are also moving through space due to Earth's orbit around the Sun and the Sun's orbit through the galaxy, and the galaxy's motion through the universe. All of that motion contributes a tiny but real time dilation to your world line. The accumulated difference over a human lifetime is negligible but physically present. You cannot perceive any of this. Inside your own frame, 1 second is always 1 second. Your heartbeat feels normal. Your coffee cools at the rate you expect. But your world line is your own. The proper time you accumulate is specific to your path. If you took a fast rocket around the Earth for a year and came back, you would return slightly younger than a twin who stayed behind. The gap would be measurable. It would be real. Your biological age would genuinely differ. And the light reaching your eyes right now, from your screen, from the lamp in the room, from the stars outside if it's night, all of those photons have traveled zero proper time to reach you. The star 400 light-years away that emitted the photon hitting your eye tonight released that photon 400 years ago in our frame. Along the photon's path, zero time passed. You are connected to that star 400 years ago by a geometric thread the universe measures as zero length. Every time you see anything, you are pulling on the light-like structure of space-time. Your vision is mediated by zero interval paths, threading the universe together. The physics in this script isn't stored in a lab somewhere. It's the fabric you're living inside right now. The same equations that correct GPS satellites describe the path your blood cells take through your body as the Earth moves through space. Time isn't a backdrop, it's personal. It belongs to your path, and your path is yours alone. There's one more question waiting, the one that summarizes everything. Where does our understanding stop? This is where the map ends. You've traveled from Einstein's patent office desk to particle accelerators, from GPS satellites to ancient photons from the edge of the early universe. You've seen time bend, slow, and compress. You've seen clocks fall behind, particles live longer, and light refuse to be caught. And at every step, the universe has been more precisely strange than the popular version let on. The slogan that started this, "Light doesn't experience time," is pointing at something real. The zero proper time of a light-like path is a geometric fact, confirmed by every experiment that tests the framework it comes from. It is not a rough approximation. It is built into the precise structure of space-time. But the slogan also imports a false picture. It gives you a photon with a perspective, a clock reading zero, a universe frozen around it. Physics doesn't give you that. It gives you a geometric path type that doesn't support the concept of a proper clock at all. The distinction is not subtle. It changes what you think you understand. This is the lesson that runs through all of physics at its edge. The precise version is always stranger than the popular version, and the precise version always turns out to have another layer underneath it that you didn't know was there. Relativity gave you flexible time. Quantum mechanics gave you the observer-dependent universe of probability. The combination of the two, at the scales where they must both apply, gives you a frontier that no theory has fully mapped. What is space-time made of, at the smallest possible scale? Does time emerge from something more fundamental, or is it truly basic? Does the zero interval of a light-like path hold all the way down to quantum scales, or does something granular take over? Those questions are open, genuinely, honestly, currently open. The smartest people alive are working on them right now, in universities and labs on every continent. The tools they're using are the same logical discipline that led Einstein from two simple rules to the entire fabric of space-time. Follow the logic where it goes. Accept what the experiments say, even when it breaks your intuition. Keep asking what the next layer looks like. That's how this script ends. Every concept locked down. Every confirmation cited. Every open question named honestly. The universe is not holding back. It shows you what it is whenever you build the right tools to ask. Light has been crossing space for billions of years. Every photon that has ever hit your eye has done so along a path the universe's ruler measures as zero. You have been connected through zero-interval threads to every light source you've ever seen, from the screen in front of you to the most ancient stars. The universe is larger, stranger, and more precise than any slogan captures, and the light crossing the room right now doesn't know what time it is, because the concept doesn't apply to it. It just travels, at the only speed it knows, along the boundary of cause and effect, stitching the universe together one zero-length thread at a time. If this journey changed how you see the sky tonight, like and subscribe. More is waiting.